everyone. In this lecture, we will discuss about the CocoTB, which is one of the emerging tool for design verification. In fact, CocoTB is one of the libraries of Python programming language. So, on that front, it is open source platform, so it's being used widely. It has some features which are really good, but at the same time, there are a lot of improvements going on in enhancement of CocoTB. Before entering to the lecture, let us understand the purpose of design verification. As far as the IC industry is concerned, there are different engineering roles that are needed right from the front end to back end. We are all very much aware that we have RTL design and then design verification. Then we have physical design. Then we have DFT roles. So these are predominant roles. So 4 or 5 roles which require major attention as far as ASIC design is concerned. On that front, design verification is the process of ensuring whether the design specification meets the implementation. Basically, when we start the IC design with any idea, so the idea must be conceived into a list of specification, and based on the specification, the RTL coding is written. RTL coding is basically written with hardware description languages mostly. The predominant hardware description languages are VHDL, Verilog, and System Verilog. So mostly the RTL design of a particular IP or a particular block is being done with the help of this hardware description language. Then the test bench is very important here. The test bench actually instantiates the actual IO port of the entire IP that has been developed, and based on the specification, the list of test cases are written to check whether the design meets the specification. The design verification is a process of developing test benches with stimulus generation and checker, whereas the stimulus generation generates various test cases which are applied to the inputs of the IP that is being developed, and then the output of the design will be taken by the checker, where a checker logic ensures that whether the expected output comes at the output or not. So design verification, a study says that almost 70% of the time that has been spent for design should be spent for the design verification, because design verification is done prior to the fabrication. Testing is done post fabrication. Design verification is done prior to the fabrication. Therefore, design verification is very important in capturing the various bugs. Therefore, there is a necessity, there is a growing demand in developing different strategies for design verification, something like that formal verification, where we adopt some kind of mathematical models for performing the design verification and all. It is always chosen, the kind of design verification platform is chosen based on the requirement, right? As far as system Verilog programming is concerned, it is called HDVL. That is hardware description cum verification language. So, system Verilog based test bench development is at the forefront. In fact, there are other open source verification strategies are also being developed. One such emerging tool is CocoTB. So in this lecture, let us try to explore what CocoTB stands for, how to install the prerequisites, and how to make the environment or platform ready for running or developing test benches with the CocoTB. And then we can also discuss about some of the use cases of writing test benches with the CocoTB. This is the lecture plan. Let us start with why CocoTB, right? Before I'm setting the context, something like ice breaking. Why do we need CocoTB? What are the various advantages of using CocoTB? And and what are the various features that can be really explored to utilize the maximum capability of CocoTB in developing the test benches? In fact, design verification is performed by developing some test benches. So it is very important to understand that concept. Then installation aspects. We'll explore about how to install the CocoTB. Especially in this lecture, I'm going to focus on Windows platform. So how to install the other libraries of Python, because as we understand basically that this CocoTB is based on Python platform. So yeah, a list of libraries are required for accessing CocoTB. Then design verification components, because in order to develop some CocoTB based test benches, let us try to understand what is the basic structure of any design verification platform. Then CocoTB design flow. uh, CocoTB is based on Python coding. The CocoTB test bench is based on Python coding. In fact, they used to call it as coroutine. And then we have our RTL code in Verilog or system Verilog. So how to bridge, how to establish communication between the Python based CocoTB and this RTL code. That is very important. A basic understanding of that interface will be discussed, and then some test bench examples and execution. Here, let us discuss one example, same design, non-parameterized design and then parameterized design. So how these two cases are handled in the CocoTB will be discussed here. Coming to why CocoTB, basically any IC design project requires design verification. Definitely, we need to perform design verification, and of course, we all know the importance of performing design verification. It can capture the bugs very effectively. As far as this particular thing is concerned, uh, we can think about functionality checking, right? Functionality checking and then latency checking. These are two cases. Especially the assertion can capture the bugs effectively. In the case of design verification arena, system Verilog has different features, because as we already know that it is a HDVL, hardware description cum verification language. Therefore, it has different features like constraints, random constraints. Then we have assertions, immediate assertion and concurrent assertions. Then coverage, right? And then because of system Verilog's object-oriented programming language capability, it can introduce a lot of classes and objects for carrying out a lot of test case development in a very structured way. Similarly, it can have a lot of inter-process communication elements, like so lot of different elements are there. So they are very much handy. And so coming to CocoTB part, right? So it's basically a open source platform based on Python, and there are like system Verilog, right? OVM. It's one of the oldest verification methodologies, and then UVM is being very widely used. In most of the industries use UVM, universal verification methodology. It uses some particular general schematic structure where you have a lot of generator and driver, right? And then stimulus generation process, and the stimulus generated stimulus goes to the DUT, and then DUT outputs the data, and then where the checker performs whether the DUT output matches with the specification or not. Then comes this CocoDB. Of course, it supports most of the features that are possible with the help of system Verilog, right? Especially random constraints or especially random generation, random input, random stimulus that can be applied here. And we can also use immediate assertions like we use in the system Verilog in the case of CocoTB. So open source is one important aspect. Another process is, so how much time is required to develop the test bench? That is important when we propose some new tool, right? Either we must have some strong we must substantiate why the tool is necessary. Since it is Python has a lot of other libraries which can help us for developing various you know functionalities. So for example, if we are developing some cryptography related IPs, we can use some crypto libraries of Python, so that the checker development time can be reduced, right? So that is very important aspect. That is one important advantage where people are looking for CocoTB. That means the checker development, almost if you are developing in system Verilog, the kind of RTL code for the checker has to be written there. But here, usage of lot of libraries, even for network stack or any other kind of libraries or mathematical libraries or statistical libraries, they are plenty available in Python. So we can seamlessly integrate those libraries in the CocoTB as well, so that the checker development time is greatly reduced. That is one important advantage I see. And then here in traditional approach, we write HDL, we write RTL with either Verilog or system Verilog, and then Testbench also in system Verilog. Now we can write the RTL coding in either in Verilog or system Verilog, whereas the Testbench can be developed using the Python environment. That is also one important aspect. So I feel that the time taken for developing the Testbench with CocoTB environment will be much more easier compared to the complex test cases development with the help of UVM or system Verilog. Of course, CocoDB is under development stage, so we cannot expect every feature that is available in UVM or system Verilog. But at the same time, we can manage. We are the good analyst to judge whether for this particular project CocoDB is sufficient for design verification or not. Right? We need every platform, but at the same time, if we are able to manage the design verification with CocoDB, that is well and good. Otherwise, we have to use either UVM or system Verilog. So in this lecture, let us focus on how the CocoDB environment is going to be developed, how the platform is really good for development of the test benches. So this is a slide which shows you how to install CocoDB on Windows platform. This is first the installation aspects are available in this particular CocoDB platform. So here we can see this here installation prerequisites. So this page is really good. So we can see the requirements, especially it requires minimum Python 3.6 plus GNU make 3 plus, because we can run the CocoDB test benches using the make command. So make is required, and a Verilog or VSTL simulator. So this one we can use any open source simulators like Icarus or something like that, Verilate or something like that. And then here if you come down, it shows the installation instructions, the prerequisites, installation commands for various operating systems like Windows, Linux Debian, Linux Red Hat, Mac OS and everything. Now we understand that it requires Python 3.6 plus and GNU make, and then we have Verilog or VSTL simulator. So in this particular example demonstration, I use Icarus installation, Icarus as a Verilog simulator. So the demonstration will be based on that particular simulator. Other simulators also can be utilized, because you can see what are the various simulator supports that we have here. So even they are supporting Icarus Verilog, and then we have Verilator, then we have Synopsys VCL, Altec Riviera. Most of the forefront the EDA tools which are helpful for the RTL design, RTL design simulation are supported by this CocoTB. That is very, very important. So now we are going to use Icarus here. So the stable version of CocoTB right now is 1.1.9.2. Right. So I'll go back to the slides. Yeah. First, let us ensure that these Python or GNU Make or Icarus are available to us. Then Icarus simulator can be installed through this particular link. This is one of the links wherein we can download the Icarus tool. Okay. So once the Icarus tool has been installed, we can check this. So here Icarus can be invoked with iVerilog hyphen capital V. So it shows you kind of license that we have for Icarus. Yeah. So it is Icarus preprocessor version 12.0. 12.0. So that will show this iVerilog Icarus version 12.0 devel. So after installation of Icarus tool, we can ensure that the iVerilog-v shows the version properly. So that ensures that it has been installed properly. After that, we can check the output files like this: iVerilog-o output file. Output file name is the one that we can give. We have RTL file name. This can be even Testbench. For example, we write a simple design, RTL design, and then Testbench. Let us say if you are developing some gate, simple gate, and then if you are writing a Testbench for that, the Testbench can be invoked here. Then VVP of that output file. So what will be the output file name that we are going to give? It will show the result. It will show the result because we are actually running the iVerilog on the test bench. So the test bench output can be displayed using the VVP command. Right? And then we have GTK wave. The GTK wave is the waveform, open source waveform generator. It can show the waveform corresponding to the input outputs that are generated through this. Now, if you come here, let us take a small example. Here, we have a small XOR gate, and there's a 2-input XOR gate, and a small TB has been developed for this XOR gate. The XOR gate has been, the RTL design has been instantiated here, and after that, a small routine, a small initial block, where we are giving 4 test cases that are not maximum possible test cases are 4. All the possible combinations are given here. It's 10 nanosecond delay. Then we are using a dump file, dump.vcd. So this dump.vcd is being used here because we want to see the output using the GTK wave. Now we are including the XOR gate here with the directive, include directive, and the timescale directive is going to set the delay time unit. So hash 10 means hash this is 10 nanosecond. 1 nanosecond is the time delay that we are setting up here. Let us run this example. So we have iVerilog -o test XOR. Then we have TB underscore XOR underscore TB dot P. Right. Now if we run VVP test underscore XOR, it will show us the output. So 0, 0, 0, C is the output, and we are input 0, 0, 1, 1, 1, 0, 1, 1, 1 and 0, which is the required output response for the 2 input XOR gate. Now we can run the GTK wave also. GTK wave dump dot BCD. We run this. GTK wave waveform viewer will open. Will show all the possible combinations that we have experimented, because the dump.bcd will record all the combinations that we have used in the test bench. Therefore, if you can see this, with 10 nanosecond delay between each and every test case, 0, 0, 0, 0, 1, 1, 1, 0, 1, and then 1, 1, 0. This is the expected response from the dump.vcd. So we are running through this GTK wave. Moving on to the next case. So we know that we have now installed the Python platform is already there. GNU Make is there. Now we have iVerilog, Icarus tool, and then GTK web. Then Conda, that is Anaconda. There is the Anaconda. We have a mini Conda setup. So because it's an open source package for a Python related environment management. So this is very highly advisable to use this, because in Windows platform, compared to the PowerShell, we can very well very easily use this kind of Anaconda Miniconda prompt, right? So it's called Miniconda prompt, which is based on the command line argument. There are two ways in which Anaconda can be used. One with the user interface. Another is this. So where it's an installer, where we can manage all the Python related repositories using the command line argument. So we will go to one example here. This is Anaconda prompt, right? So it will support us all the commands that are required based on the Linux operating system, and based on the requirement we can use those commands, right? So here we can install the Python already available here. So Python 3.6, right? So we can install some tools like this. Pip install CocoTB. Pip install CocoTB. So it will show whether the installation is successful or not. It will show if the installation has been already done. It says all requirement is already satisfied. So now we have installed CocoTB 1.9.2, which is the very latest version, and we can also check whether CocoTB is properly installed or not. CocoTB config -- version. So this will show you 1.9.2. So this should show, we have to first check this CocoTB underscore CocoTB -config -version. So this should match with whatever be the version that is installed. Another thing is we can install pip install pytest. So this is another package that is important for running the different test cases with CocoTB. PyTest is very important for us. So once you are installing PyTest, it will install other required packages along with that, ini config, packaging, pluggy, and whatever it may be. And if required, we can also install NumPy and other things also, Matplotlib if required, or crypto libraries, whatever it. If we want to install those things as well. So that will really help us to explore the CocoTB's utility in various other requirements, especially when we are developing the checkers. So this is a requirement. So in Windows platform, this is Windows 11 platform, Windows 11 OS. So we have Python 3.6, we have GNU Make, we have the Icarus tool, we have GTK wave, and then we have CocoTB installed with the pip, CocoTB, and then PyTest. And all these things, the Python related packages are being managed with the help of the Anaconda prompt. Right. Now moving on to the next stage. So now coming to CocoTB software interface. So CocoTB uses a set of libraries, so where we have to import those libraries for writing our test benches. So the test cases which are developed using CocoTB are called coroutines, because coroutine, right, in fact, coroutine based co-simulation test bench is called CocoTB. Coroutine based co-simulation test bench. So all the test cases are called coroutine. So what these test cases are capable of? They are capable of running clock. They are capable of applying inputs to reset. They are capable of applying reading the inputs or writing. Writing to the input port and reading from the output port of the design, right? And then so this is entirely a Python code we have to write, in which we are going to invoke, we are going to utilize the CocoTB libraries and the objects of the CocoTB for developing various test cases, because this is more hardware oriented. For example, we have to match with the timing also. For example, we should apply a particular we should generate a particular clock with this much on time and off time duty cycle. We should be able to create this much amount of delay in the hardware. So many things are involved in this. So there should be a communication between your CocoTB and then your DUT, that is design under test. Now design under test is mostly written with the help of Verilog or system Verilog. Now how this communication happens, that is based on the GPI, that is generic programming interface. And the generic programming interface is capable of communicating with Verilog programming interface, VPI or VHPI, VHDL programming interface, or foreign language interface, FLI, right? So GPI is the middleman which communicates, which translates the requirement between the CocoTB and the DUT. So now the process happens like this. The coroutines are generating the inputs to the DUT. DUTs take the input and they generate the output, and the output is going to be read by the coroutine, right? So after that, that checker is going to be done in this. So whatever be the functionality of Testbench that happens on the system Verilog platform is now going to happen on the Python environment. So this is a design verification component structure. So as we know that the design under test, the stimulus generation generates the possible inputs to the DUT and they apply to the DUT, and then DUT generates the output. The checker compares whether the output is expected or not, whether there is any deviation with respect to the output that is generated from the DUT and the actual expected, whether actual and expected are equal or not. That should be ensured by the checker. Now so there is an example of coroutine structure given here. At cocotb.test, every new test has to be written with at cocotb.test, and then we have the coroutines start with async def. Def we basically use for writing the functions in Python. Async def. Every coroutine should start with this async def. A coroutine can be called inside another coroutine also. I mean, a function is being called inside another function, something like that. You have to assume that the coroutine is a kind of function that executes a series of steps to perform the particular test. Every test has to be differentiated with the help of at cocotb.test. Right. Now we use a handle called DUT. This is a fixed one. We have to use it as a DUT only. It's a handle supported in CocoTB. So with the handle, we can apply various objects onto that. DUT dot. So the DUT handle allows us to utilize the IO ports of the DUT as objects. DUT.A, DUT.B, DUT.C. So A and B may be inputs or outputs. So when you are forcing the value to that particular object, DUT.A equal to 0, that means you are applying some input to the A. That means you are the coroutine is going to output a value which is going to be the input to the DUT A input. Then await is also another function which is helpful for parking a particular execution. So that is a control structure. Wait till the timer completes 10 nanoseconds. That means you are applying input. After that, you are introducing a delay. Then you are applying input. introduce the delay. This is the process of writing test benches. Now the delay can be a fixed delay or can be based on the clocks. For example, we can introduce one clock cycle delay or two clock cycle delay. Whether the clock has to be delay has to be controlled based on the rising edge of the clock or falling edge of the clock. These are the various options that we have. Then assert. So for example, this is AND gate example. So when two inputs are 0, output should be 0. So for example, dut.y dot value should be 0. If it is not, it should display a message like failed when a equal to 0, comma b equal to 0. Now with respect to CocoTB design flow, so we have various aspects like declaration of modules where we have to import them. So import CocoTB. From CocoTB.triggers import falling edge, rising edge, timer, then import OS, and then these OS are required for test runner, right? Test runner is something like a wrapper which uses various file names to link the CocoTB file and then the DUT file. So it's a wrapper where that is where we need the use of the file names and all. Then accessing the design and signals, right? As we know, handle, right? We are writing cocoroutine. The cocoroutine actually call the handle DUT, and inside the DUT we have lot of objects like using the dot object attributes, because Python is it's a well-known fact that Python supports object-oriented programming. So dut.a equal to 0. That means we are writing input from the CocoTB. Y equal to dut.b. That means we are reading output value from the DUT to CocoTB. Then coroutine. So an await will run async coroutine and wait for its completion, right? So for example, inside the coroutine we can call another coroutine. We are writing, for example, any clock generation process separately as another coroutine that can be called inside another coroutine. Then logging, whatever be the inputs or outputs that should be displayed properly, for that logging is required. So declaration of module, declaration of various libraries, then importing them, then writing the input, reading from the output, then utilization of coroutines, logging. These are major blocks in every CocoTB test bench. Some design examples, like next we'll discuss about, we'll see some demonstrations based on non-parameterized and parameterized design. Then files required for full design verification with CocoTB. What are the minimum requirement if you want to run the CocoTB? You need one RTL file, which is DUT, which is mandatory. Then we are going to write one test bench file, that is .py file, right? So RTL may be .p or .sv. Then the test bench file .py, and then make file or test runner.py. Make file has some limited parameters that can be called. Then .py library files are optional. If you want to write some libraries, and we can include those things in the test bench file. If it is required, we can make use of this. So mandatorily, you must have a DUT, you must have a Python CocoTB test bench, and then a make file or test runner file. So these three files are mandatory for running any example. Let us get into one small example of running a small counter. This is the counter code. This is a 8-bit counter, up-down counter, written in system Verilog programming. It uses the inputs clock, reset, and up-down. When up-down is 1, count is incrementing. When up-down is 0, when up-down is low, the count is decrementing. So up and down are controlled by this up underscore down input, and then output is CNT. It's a 8-bit count, so that varies between 0 and 255. Now going to the test bench, CocoTB test bench. So here, as I already told you, we have to import the CocoTB. Then from the CocoTB triggers, I'm going to use these control units like falling edge, rising edge, and timer. Then we have clock generation, because the counter has to run based on a particular clock. So this coroutine is generating the clock. Async def generate underscore clock. This is our own name. DUT is the handle that we already know. So here we are running one loop. So we are going to generate 500 clock cycles with 10 nanosecond as the clock duration, with 50-50 duty cycle. That means 5 nanosecond on, 5 nanosecond off. DUT dot clock dot value. This is how we have to access the object, because clock, RST, UP underscore down, and then CNT are the signals that are available in our counter DUT. All these things can be called here with the help of the DUT handle. So await timer, right? So that's a real timer. We can give the units as nanosecond, picosecond, or everything. So this particular loop runs for 500 times, 500 clock cycles it will generate. Now I'm going to run two tests. One test is for up counting, another for down counting. So again, one Coco routine I am writing async def, my first test of DUT handle. So as I already told you, every time if you write at CocoTB.test, it will be considered as a separate test. Await CocoTB.start, because we are going to start the clock. CocoTB.start, right? So here we can do any schedule a coroutine to be run concurrently. So this will be right concurrently running. So parallelly it will run. It won't disturb that. That means when we are starting this, it will run continuously. Right? That is a requirement here. Right. So generate clock of DUT. So generate underscore clock is here. So we have to use the DUT here. Are there any arguments? If you are using any inputs there, we can also call here. Then some small delay is introduced here. Now reset, when the reset is zero, what happens? The count is reset to zero. So the same process is happening here. So, and then up down is made as 1, because this is a up counting process. For I in range of 100, right now I'm running for 500 clock cycles, but here I'm going to run it for just 100 clock cycles. It can be run for any number of clock cycles, because the up counter, once it reaches 255, it is going to reset again 0 and continue the execution. So DUT.log underscore invo, first every falling edge, during every rising edge of the clock, counter is going to increment, but it will be stable during the falling edge, right before the next rising edge. I am reading this, so data will be stable during the falling edge. That's why I am waiting for falling edge and then reading it here. And here one small assertion, whether the increment is properly happening or not. So DUT dot CNT dot value I am reading here 0, 1, 2, 3 like that. For example, odd numbers will be stored in the A, and even numbers will be stored in B. For example, first number 0, 1. So what happens is, now I am checking whether B is equal to A plus 1. Increment is properly happening or not. This is the condition. Assert, ensure whether B is equal to A plus 1. Otherwise, increment is not correct. Okay? Hope you understood this. Same thing at CocoDB.test, async def, my second test. This is a name that we can give of DUT. Again clock generation happens here. At CocoDB.start, generate underscore clock of DUT. Again 5 nanosecond delay I am introducing. Reset value becomes 0. Reset. So I have just reset the counter. Up down value is 0. Now it has to decrement, right? So here also it's going to run for 0 to 98, 99. Then again, as this in the same case, just a difference between the test case 1 and this is up down value. Up down value was 1 there. Here it is 0. Now, in order to avoid a particular test case, I start the assertion after running first cycle. So when it becomes 255, 254, 253 like that, so I am checking whether B is equal to A minus 1. So increment is correct or not. During that case, we can check very well. Now now we have written the Python script, CocoTB script. moving on to make file. So in this make file, this is a structure. This make file is already available in CocoTB repository, CocoTB page. That was already shared with you. Same thing can be used. Here we can give the sim as Icarus simulator. Top level language Verilog. Verilog sources, the present working directory counter.sp. This is a top level language. The top level module in our Verilog counter.sv. Counter.sv has counter as the module name. Then we have test underscore counter as the this CocoTB file name. Test underscore counter is a Python test file name. That's all. Need not do the modification, any modification. So make file. Let us run this make file with this counter. Right. So here we are going to run the make file. So the make file establishes a link between our CocoTB file and then the DUT, because it represents all the file name, Python file name also, and then it uses a module name, RTL module name, and then RTL file name also. So this make file will run both the test cases and it will display the output for every time. So every clock cycle we are incrementing it. So 10 nanosecond, every 10 nanosecond, what is the output it has to show. So the first test case is the up case where the increment should happen, and during the second test case the decrement should happen. So every test case will use one random seed, right? Even if you don't give, it will use a random seed, or we can apply the random seed. For example, sending Python random module with this. This is a random seed taken by the CocoTB itself. We can also check this with change this with the parameters, and then now you can see this every 10 nanosecond, 20 nanosecond, 30, 40, 50, like that. Counter is incrementing. It goes from 0 to 99. It's the first test case. Down counter is there. So 255 to 158, because we are running close to 100 test clock cycles, right? So yeah. So here also increment happens during every 10 nanoseconds, which is expected response. Now we can also give some things like this. Make waves equal to 1, random underscore seed equal to 1, something like that. Waves equal to 1 represents creation of a .fst file, which can be used for viewing the waveform. The .fst file or .vcd file can be viewed using the GTK wave. So here these are parameters. There are many supported parameters that can be possible. The CocoTB link will show us what are the possible parameters that can be set. So those things can be really understood with the help of this CocoTB documentation link, right? Yeah, so it has now run this. So now if you can see this seeding Python random module with supplied seed 1. Right? And now we can also see this FST file, sim.vvp hyphen FST file. So it has generated that. So we can also see vvp sim.vvp. So yeah, now GTK wave counter GTK wave, it will be available in sim underscore build counter dot fst. So now it has opened the counter, so it shows all the signals that are available to us. So every counter, the clock cycle, it's taking the clock cycle. So every 10 nanosecond, 20 nanosecond, like that. So it's running this. The total clock cycle duration is nanosecond. So every positive clock cycle, positive edge of the clock cycle, it's capturing it. So 0, 1, 2, 3, 4, like that. And then after running 9 up to 99, again we are resetting it. Yeah, we are after running for 99, we are resetting it. So this is showing in hexadecimal. We can show it in decimal. So after 99, so now it is being reset. After that, it begins from 55. So this is a FST file. The FST file will be present in the sim underscore build directory. This will have the sim underscore build. So we are in counter test. So this will have sim underscore build directory. So this will have the counter.fst. Right. Now, next example is how to utilize the test runner for this. Right. So test runner is another approach where it has a lot of flexibility, like writing that in a log and other things. Like it also has some specific structure. We have to write it. We have to use sources. We have to give the path of the DUT file. Then get underscore runner. Then we see this. Yeah. So we can see this runner equal to get underscore runner of sim runner dot build sources equal to sources HDL underscore top level counter. So this is a counter is a partial module name. Always true. In true, it will clean the logs and other things. Waves equal to true, that will generate the FST file. Verbose true, so it will display the output here. First thing is this import OS, import paths. Then we are writing inside the function called test underscore runner. That's why it's called test underscore runner dot py. Now runner dot build should be written, then runner dot test should be written. So here not many things required. So here I have commented log file, log underscore file. Otherwise, if you use the log file, it will be present in build.log. HTML underscore top level counter, test underscore module. So test underscore module represent the Python name. So here also it's called the top level module, right? In the case of make file, you see this HTML underscore top level counter, test underscore module. This name should be maintained as such. Only the right hand side name should change based on your file names and module names. Suppose true, waves true, and here is a direct test running. There are two ways to run this: direct test and PyTest. Okay, it's a direct test that we are running it. If underscore name equal to main. Otherwise, we can use at pytest dot mark dot simulation. Now, the test runner provides us lot of other parameters. That is the difference between make file and this. Many parameters can be called inside runner dot build and then runner dot test. Finally, calling this test underscore runner function. Right. This is a test runner dot. So how to run this? So we use Python test underscore runner dot. So now it is running the test runner dot py. Okay. Now if you use pytest, it will also run in fact. Right? But basically, if you want to display this based on the directed test or pytest, we can choose this. So for in the PyTest also, it will generate right in the test runner based test also, it can generate the GTK wave because we said the waveform has to be generated because we have enabled waves equal to true, so it will generate the waveform like you have seen, right? So this waveform is also generated here. So moving on to this is a non-parameterized design. Moving on to parameterized design, we have a same counter, counter with a width as a parameter because the output width is now controlled by the parameter width. Others are same in the code. Now if you come to the counter parameter code, it remains the same because it calls for the width. It calls the width here. Entire the old code is completely same. Only thing is we are calling the width here, but the parameterization has to be properly defined. Parameterization has to be properly defined inside the test runner. Now you see this. In the old case of test runner, there are no arguments inside this. So test runner, open bracket, close bracket. Now we are going to use a parameter called width. Now this test runner should have this width, test runner of width int equal to 0. And after that, declare this parameter width equal to width. And then coming here, parameters equal to parameter, especially you have to write it inside the runner.build. You can have multiple parameter. All these things can be written with separated by a comma, width, size, something like that. So first thing is you have to declare the parameter here. Then define this parameter width equal to width. Then here you have to write parameters equal to this parameter, whatever you have written here. So runner.build will actually understand what parameter we are going to use. Then no change in runner.test. Coming to directed test, there are two ways to run this. One is through PyTest, another one is through this. In the directed test, you can run for width in 4,8. These multiple options we can apply. That means DUT parameters can be, when we are running the test bench, we can test the RTL design with multiple parameters. This is the use of parameterized testing. Now test runner equal of width equal to width. So this is a direct run. This is a PyTest run. Both these things we can do this. So counter parameter we have to parameterized counter. Then we have so when we are calling the parameter here width, especially for computation or for size, because the size is going to change, so based on the width value, we are going to increase the number of cycles. So we are calling it inside. So the test counter param.py, which is the actual CocoTB test bench, is calling this width. So this link between this and the RTL file is established through the test runner. So this entire definition is required for parameterized testing process. Now we are testing for two widths. One is the for width equal to 4, another width equal to 8. Yeah, it's going to run a couple of tests. First test, it is running for width equal to 4. You can see this width equal to 4. So it varies from 0 to 15 and then 15 down to 0. It's a second tester. And now coming to this particular test process where width is equal to 8. Now 0 to 55, it's going to run. Right. So this is how this testing is performed with the help of parameterized testing. Now we can comment this can comment this whole, and then instead let us run this with PyTest. So the difference between PyTest and this is, you see here in the directed test we have to use if underscore name underscore equal to main. So here we have, when you are using the PyTest dot mark dot parameterize, it is also the easiest way. But instead the definition name of this you should use different name for this. But test underscore runner width equal to width, whatever we are calling it here, that should be written here. So we'll run pytest test underscore runner dot py. Yep. So it's passing this. So that is also another way to view our result. So in this way we can run many test cases using the CocoTB. So we basically understood how to develop the test test cases, test bench using CocoTB, and how to handle non-parameterized design, how to handle parameterized design. So basically DUT file, then a Python code for CocoTB test bench, then a make file is needed. In the absence of make file, we can also use test underscore runner dot py file. So this is a couple of examples based on the counter design we have understood in this particular lecture. Thank you.